Hi everyone, Mr. Fugay here. This video is going to be the first of three parts actually that we're going to look at the concept called related rates. So we're going to start with this problem here on the screen, and this is actually the last problem we're going to cover in this video. And it talks about a ladder leaning it vertically against a wall. So here's the wall here in our ladder. If the bottom of the ladder slides away from the wall, so if you pull the ladder away at a rate of 2 feet per second, how fast is the top of the ladder sliding down the wall when the base of the ladder is 5 feet from the wall? Let me ask a more general question. If this ladder is going to slide down the wall, clearly the distance it is from the base and the distance it is from the top is going to change. So how far the bottom of the ladder is from the bottom of the wall and how far the top of the ladder is from the bottom of the wall. And the question I have for you is I hit the play button here. Are the rates of which, how quickly that's changing, are they actually the same? And what you might be seeing here in the beginning, not really sure. H and X are definitely, if I pause here, X is definitely getting bigger. H is definitely getting smaller, but as we continue to watch this, they might look like they're growing and declining at the same rate, but here at the end, this is very interesting. X is barely changing, but H is changing really drastically. And I'm going to take that slider back a little bit and just show you. So they're not changing that much, but X, if you notice, is not changing much at this point, but H is. And so these two rates are variables. They are varying with each other. H is definitely growing at a different rate here than it is down here at the bottom. And so our job here with calculus now, knowing that we've been studying rates and rates of change, is can we relate these rates to one another? And the way that we're going to relate these rates to each other are using different formulas of relationships that we already know. So you already have access to this formula sheet here. This is a bunch of geometric formulas and formulas just throughout your math career that you've used over time, and we're going to be using these in context of other problems today to relate the rates of things to one another. So without further ado, let's go ahead and let's start with some questions here. Before we start, here's a general process that I'm going to use as we go through this. I want you to pay attention to my logic and thought as we go through some of these. We're always going to want to draw a picture or have some type of visual aid to help us. We want to then make a list of all of the unknown rates and quantities that are given in our question. It's also important to identify what things are constant. Remember that constant things won't have a rate to them. We're going to relate the variable in a known equation, so that's where those formulas are going to come in. We're going to look for a relationship of something we've already learned in the past to relate them to one another. We'll then substitute any constant values, and let's be very clear what constant values are different than known values, and we'll talk about that in the questions in a minute. Then we'll take the derivative with respect to time, and we've already talked a little about that with some of the formulas that you guys done previously. We'll substitute things in and we're done. We're solved. So if we start with the very first question here, we talk about a square is increasing in size. And again, there's a very quick visual here on this as I'm going to press play. Here's your problem. And I'm going to go ahead and press play. So a square is increasing in size. Its side length is growing at a rate of 3 inches per minute. So this side length is growing 3 inches per minute. When its side length is 9 inches, what is the rate of change of the area dA dt? So that's what we're going to be asked to look for in this very first question. So again, you have your square here drawn, and we know that we need to look at something regarding the sides. Now, whenever you see the word rate, it's relating to the side length. So that's going to tell me that a rate is going to be some type of derivative. So in this case, it's going to be the change in the side length with respect to time, or ds dt. And since it is growing, that means it's getting bigger, so its rate's going to be positive. So we know that it's a ds dt. They want to know when the side length is 9 inches. Now we'll talk about this in a minute. When the side length is 9 inches, what is the rate of change of the area? If we want to know the rate of change of the area, that's going to be denoted by dA dt. So we'll go ahead and we'll write that in. And I'm just going to put a question mark here. So what I've done is I've drawn a picture. I'm going to go through my list. Make a list of known and unknown rates, quantities, and they're given. And we need to look for a relationship. So is there a relationship that we know from our mathematical dictionary of things, or a thesaurus of things, that we can pull from? And the answer is yeah, we have the area formula. The area of a square is just A equals S squared. Now, really important thing here before we go ahead and we try to take the derivative of this, are there any constant values in this question? And some people will look at this 9 and go, oh yeah, the side length is 9. But that's the side length at a given moment of time. So we're analyzing rates at a given moment of time, what I would like to call a snapshot, all right? we're taking a snapshot of something that's actually happening. So in the case of the ladder question that we're going to come back to at the end of the video, when the ladder was falling down the wall, the length of the ladder never changed. So no matter how much I slid these things or changed this ladder, that 13 never changed. That's what I mean by constant. But at any given moment of time, freeze frame, X and H are going to individually be some value. So just because we have a value for it doesn't make it a constant. The question is, over the course of time, as you play out the scenario, does that value change? And in the answer of the square question, yeah, the side length is going to change based on our visualization. So that is not a constant. So we're going to go ahead and take the derivative of this. So we're going to get dA dt equals the derivative of s squared is 2s, and then we took the derivative of s with respect to t. So here it is. This is what we've been doing all along. This is our related rate. And now we can substitute what we know to help us solve for dA dt. So let's do that now. So dA dt equals 2. We now can plug in that s is 9. We know that ds dt is 3. And so when I simplify this, we're going to get 54 square inches per minute as my final answer. 54 square inches per minute. All right. So why don't you take a moment after looking at this first example, and I would like you guys to pause this video and try example 2. In this case, we're looking at the area of a circle instead. Okay, welcome back. And in this, here's our answer. We got 30 pi square inches per second. We didn't talk much about the units. I sort of just wrote them out without talking about it in the last example. But keep in mind that we were looking for the area with respect to time. And so our units are going to be area and time. So you just take whatever units that you're using for your derivative value, and that tells you what the units will be for this question. So they gave us dr dt because they talked about the radius growing at a rate of, and then they also told us at the moment when the radius is 5. Once again, the 5 is not a constant because the 5 is changing over time. That is simply just a snapshot of what's actually happening here. So there's going to be our answer for example number 2. Now, let's talk about a time where we are actually going to have a constant, and that's going to be in this situation here, example 3. So we're looking at drought conditions in a town, and they're withdrawing from a cylindrical reservoir. So we're looking at a cylinder in this question instead. So something a little different, okay? And the radius of this cylinder is 4, okay? So there's our radius. So I'll go ahead and write that R equals 4. The height of the empty cylinder is 10. Now, we're not going to write that down because we're actually talking about water level when we get to later in the question, so I'm going to wait to write that down. But the volume is changing at a rate of 5 cubic feet per minute. Now, keep in mind that they are withdrawing. So some key words to look here. If you're withdrawing water from something, that means you're losing volume. So in this case, this is going to be dV dt. And again, I knew it was volume because it was cubic feet per minute. This is going to be a rate of -5. How fast is the water level dropping? Now, when we talk about the water level, here's the water. Water level is actually referring to the height. And so the related rate that we're looking at is actually not the cylinder, the canister that it's in, but actually the water, which is shaped as a cylinder. So the volume of a cylinder we know as pi r squared h. Now, what's really important in this question to understand is that we actually can't take the derivative of this without using product rule, which in the event of the radius and the height both changing and being variables, then yeah, we're going to have to do that. But the key here is no matter where the water level is at, the radius of this cone, look at where the water levels would be here. All the radii are going to be 4. So this 4 number, no matter where I put, oops, that was supposed to be a highlighter. No matter where I put the water level will always have a radius of 4. So one thing I can do in this question that I haven't been able to do to this point is I'm going to be able to actually plug in the radius before I take the derivative. And the reason why we can do that is we can now, it's not changing at all. So we're going to go ahead now and we can take that derivative. So this is going to become dV dt. Oh, this is 16 pi. So the derivative of 16 pi h is just going to be 16 pi dH dt. So there is our related rate, okay? Our related rate, and we can now plug things in. Notice that the actual height, because they actually are asking when the depth of the water is 6 feet. Keep in mind, a little bonus question for you to think about on the side. Notice that it doesn't matter actually what the water level is. So think about why that might be, and that's a great question if you're not sure the answer to ask me in class. Why does that height not matter in the grand scheme of things? But because there's no h in here. So let's go ahead and we're going to plug things in. So we know, oh, actually we know dv dt in this question. We actually are going to plug that in as -5, okay? And then we're going to go ahead and plug in the 16 pi. dh dt is what we're actually trying to solve for. So if I divide both sides by 16 pi, I get -5 over 16 pi is my dh dt. And when you simplify that, we get a very small number, -0.099 feet per minute. And that's going to be my dh dt. If they were to ask you to analyze this question, okay, and create some kind of analysis for this, I would say that the water level is dropping at a rate of 0.099 feet per minute. Keep in mind that the negative is referring to direction, right? So the water level height is dropping, and that kind of makes sense. If the volume is dropping, so will the height of the water. It will drop there, okay? Next question, example 4, the last of the volume questions, and then we'll come back and we'll tie everything in with the Pythagorean theorem question. So this now brings in the idea of a spherical balloon. And what's going to be a little more challenging in this question is that it's telling me what the dv dt rate is right here. So it's saying that dv dt is 60 pi. Then it says how fast is the surface area. Ooh, okay. So now we're asked about how fast the surface area is expanding. So we'll go ahead and we'll call that maybe dA dt. That's an unknown. Now the challenge with this is there's no formula that relates volume to area. So we're going to actually have to look at two different formulas and try to build our problem from there. What is going to be true regardless when we look at the volume of a sphere or the surface area of a sphere is that they're asking us at the instant that the radius is 4 inches. So we're going to still go ahead and write r equals 4 under both of these scenarios. But what I want to challenge you to do right now is to pause this video, and I have two formulas here. Volume equals 4/3 pi r cubed, and then area, try that again, area equals 4 pi r squared. So we have two formulas, and I have two different things here. Take a moment, pause this video, and see if you can figure out what you might need to do in order to finish solving this question. It will involve taking two derivatives. I'll give you a moment to pause that. Okay, so after pausing here, if you got stuck and you just wanted to play and see what the answer was, here's a quick hint to help you. In blue here, what I went ahead and did is I took the derivative of volume because I already knew what dv dt was, and I knew what r was. So I kind of figured I could solve for dr dt here. And this dr dt, ladies and gentlemen, is going to be the link that's going to allow me now to solve for dA dt in my next question. So what I would do now is go ahead by plugging this in, by finding dr dt as 15 over 16, we're now going to take that and we're going to plug it in to the derivative of the surface area, which is the problem here on the right. So once again, I'll give you a second to pause this video and see if you can finish the problem off. Okay, and here's the wrap up of example 4. So in example 4 here, what we did now is we finished up. Since I knew what dr dt was from our volume question, I went ahead and plugged that into the derivative here of the surface area, and we knew what the radius was 4, and we plug it in to get our answer as 30 pi square inches per second. Just as, again, another reminder that there was no constant values in this question because, again, the radius was always changing when the spherical balloon was expanding, so we weren't able to substitute anything until after we took the derivative here, okay? We're out of time on this first video. We're going to wrap up on another video here immediately after this. That is going to be the Pythagorean theorem, which was the question we started the video with, and that'll wrap up for the last couple minutes. I'll see you on that video in just a moment.